According to our model of consumer behavior, consumers maximize their utility subject to their budget constraint. We can represent that process on a graph like this one. The green line represents their budget constraint, showing us what combinations of the two goods X1 and X2 are affordable. The orange curve represents an indifference curve, and every point on it would give this person the same level of utility. If we push the indifference curve out, we increase utility. And so the highest possible indifference curve, which still has at least one affordable option on it, will allow us to identify the best possible choice for this consumer. It will be their equilibrium. So what can we learn from this? Well, we'll skip some of the fancy math and jump right to an important conclusion. At that point, this fact is true. The marginal utility from X1 divided by its price will be equal to the marginal utility from X2 divided by its price. This is what we call the optimal consumption rule, which says that to maximize utility, a consumer should allocate spending so that the marginal utility per dollar is equal for all purchased goods. I like this rule because it helps me think through decisions about how much to buy. Do I want the fastest internet package offered, or is the mid-tier one best? Should I pay for that extra feature in a new car? Should I buy things in bulk or one at a time? These are all questions where the optimal consumption rule is the best guide to the answer. So let's explain what exactly all this fancy math means. Marginal utility is the change in utility from one additional unit of consumption. Marginal is a really important word in economics. We're going to use it over and over again because one of the most important insights economics has given the world is the importance of thinking on the margin when trying to make optimal decisions. Here's an example of marginal thinking. An economics student and a philosophy student go to a party where there's cake. I love cake, says the economics student, who takes a piece and digs in. I can't help but notice, the philosophy student interjects, that after finishing your cake, you didn't take another piece. You said you love cake and more cake is available. Isn't it irrational from an economic perspective for you to not satisfy your utility and have another piece? The economics student smiles. Of course not. I get lots of utility from the first slice, but the marginal utility of having one more slice is lower than that initial slice, and now it isn't worth the cost to me. I love cake, but there are trade-offs, and if the utility of the next piece isn't high enough, I won't consume it. Marginal utility is important because it's how we understand when people stop doing something. Everywhere we look, we see diminishing marginal returns. If I give you one speedboat, you'll probably get a lot of utility from it. If I give you a second one, your thanks might be a little more muted. 2 speedboats, it turns out, does not give you double the happiness of 1 speedboat. And a third would give even less than that, and still less for a 4th and a 5th. It isn't that getting more speedboats is bad. You'll probably find a way to use them all, but the utility you get out of them is diminishing on the margin. Each additional speedboat gives less utility than the one before it. If we chart out this marginal utility, we see that it is diminishing, and that reflects our law of diminishing marginal returns. We've already seen marginal utility in action with our utility functions. Let's say our utility is given by x1 times x2. To calculate marginal utility, we must hold one of the two goods fixed. So we will hold x2 at a value of 1. A table will help us see how utility changes when we increase our consumption of x1, holding x2 constant. If we get 1x1 and 1x2, we will have 1 unit of utility. But if we get 2x1 and 1x2, we will have 2 units of utility. The marginal utility of x1 is the difference in utility due to a 1 unit increase in x1. So going from 1 unit of x1 to 2, our utility went up by 1 unit. And indeed, if we calculate marginal utility at these other steps, we see it is 1 every time. In this case, our marginal utility is not diminishing. It's constant at 1. What if we increase our value of x2 to 2? Does that change the marginal utility of x1? It does. Now, each additional unit of x1 increases our utility by 2. So the marginal utility at each step is 2. And this change happens again when x2 is equal to 3. Now, 3 is the marginal utility of x1. If you've taken any calculus, this won't surprise you. We find marginal utility by taking the derivative of the equation. But you don't need calculus to see the result for this utility function. The marginal utility of x1 is equal to whatever value we have for x2. And this will be the same for x2. The marginal utility of getting 1 more unit of x2 will be equal to whatever the value is for x1. Because of how simply this works out, you'll want to remember it for quizzes and test questions, which will feature this same utility function. But when in doubt, you can always make a table like this one here to calculate the marginal utility. This is useful because it helps us to mathematically solve the buyer's problem using the optimal consumption rule. Let's define this consumer's utility as x1 times x2. We will also give them $20 to spend, where x1 costs $2 each and x2 costs $4 each. What should this consumer do? We start with the optimal consumption rule, where we equate the marginal utility per dollar. We know that the marginal utility of x1 is x2, and the marginal utility of x2 is x1. We also know the prices of x1 and x2, so we can plug all of these values and variables into our optimal consumption rule. So now we would have x2 divided by 2 is equal to x1 divided by 4. Let's rearrange this equation so that we have it all in terms of x2. x2 is equal to 2/4 of x1. Now we can use this equation along with our budget constraint to solve. Our budget constraint is that 20 equals 2 times x1 plus 4 times x2. And we know we want to pick something on that line. We also know in order to optimize, we want to pick x2 so that it is 2/4 of x1. So we substitute one equation into the other and solve. 20 will be equal to 2 times x1 plus 4 times 2/4 times x1. I am just plugging in my expression for x2 into the budget constraint. These 4's cancel out, and we can simplify to 20 equals 2 times x1 plus 2 times x1, which simplifies further to 20 is equal to 4 times x1. That means x1 equals 20 divided by 4, which is 5. This consumer is going to choose 5 units of x1. To find out how much x2 they will buy, we just plug this back into the budget constraint and solve for x2. 20 equals 2 times 5 plus 4 times x2, which means 20 equals 10 plus 4 times x2. We can subtract 10 from both sides to get 10 equals 4 times x2, which means x2 equals 2.5. As foretold by our equation for x2 before, we're getting a value for x2 that is 1/2 or 2/4 of x1. This step-by-step process allows us to find the equilibrium point for the consumer when we're given their utility function and budget constraint, which is pretty neat. It also corresponds to our graph. What we found is that this point, where the indifference curve is tangent to the budget line, is at the coordinates 5, 2.5, or where x1 is equal to 5 and x2 is equal to 2.5. I know that many of you are a bit repelled by math or think that math just isn't your thing, and so this video has been a bit rough. But I promise this is all well within your capacity. You can absolutely understand all of this if you put your mind to it, and taking the time to work through it will help communicate the many insights this model has to offer. And so I recommend this to everyone, comfortable with math or not. Take some time right now to make yourself a note card that walks through the steps you need to take to find the consumer's equilibrium when given a utility function, income to spend, and the prices of the two goods. It'll be worth it. And you'll see that the more you practice it, the smaller this problem gets.